So next, I want to talk about sort of the workflows of how you do all of this, and the question is, so how does this all help? So what you're going to do is you're going to take all this knowledge of stress strain curves, and you're going to put it into these workflows. You're going to do this analysis, and you're going to come out with a useful number at the end, a useful image. So next up, we can see sort of the overall workflow for selecting FEA or CFD within these programs. Next slide. So here, you know your goal. So for instance, it could be had to save material or increase durability. Maybe you care about the fluid flow, and from that you can choose whether to do a fluid flow analysis or solid body analysis and other things. Once you decide upon, that's fine. Once you decide upon solid body analysis, you're going to use another workflow within the program. So that's the next slide. And that workflow is shown here, but I'm actually going to step you through, so we're not going to cover this right now.
And so these diagrams are available on the Autodesk Sustainability Workshop website, and the intent behind them is to help step you through in a strategic process to help you use these types of tools on your design projects.
Yeah. So the first step is you're going to figure out what you are analyzing. So in this case, in this example, we're going to analyze a brake pedal from a race car. And the first step after that is to take away all the superfluous pieces. You just care about the piece that you're really trying to analyze. So in the next slide, you can see what that looks like with most of the things removed. Now we only have the cage and the pedal itself. That's good. So that's a good first step for an assembly analysis. So next slide. So in this step, you're going to do contacts. So this is only for assembly analysis. If you're just analyzing one piece, you won't need to do this, but this is automatically done by the computer, and in certain situations, you'll need to go through manually. But that should be pretty intuitive, hopefully. So next step.
There's a little bit of a lag. Shaquille's in France advancing the slides, and the electrons need to work their way across the ocean.
So the next thing you're going to want to do is assign material. And as I said before, a stress strain curve is different for every material, so it's really important that you use the right material, that you don't just say, oh, it's aluminum or it's steel or something. You get the right one down. And this is going to be important for your factor of safety as well. So after you've assigned materials, the next step is to add constraints. So in this case, there's a pin constraint and a frictionless constraint, and we'll just step through these two really quickly because it's a bit of an odd example. But you want to make sure that you add constraints. Just as you added forces that would be real, you're going to want to add constraints that are real and reflect what's actually going on in real life. You don't want to just fix everything and say, well, that's good. You don't want to over-constrain your part, and you don't want to constrain it in sort of fictional ways that will give you an incorrect result at the end. So in the next slide, what we're going to do is actually add the forces. And so the first force on the face, and then in the next slide you can see the forces. We know that there's a cylinder down at the bottom pushing the other way, so we're going to add those forces. And again, these forces, just to reiterate, are found in real life. You have to go out and actually test to see what your forces are going to be. You can't just guess at them. Or in certain situations, there'll be a standard number that you have to use. The next thing is to generate the mesh. And the mesh is how the program breaks the problem down into smaller pieces and then solves them all together. So each of these blocks is essentially going to be solved with relation to the blocks next to it and all of those blocks, the ones next to them, using complex matrix math. And so this is how it's broken down. So the next thing we want to do is analyze that mesh. We want to look at it and see, well, does this look good? And you can see here that it's pretty blocky. There's weird aspect ratios. It doesn't really look quite right. And this is something that you'll develop over time, the ability to understand whether a mesh is good or bad. But from looking at this, you can pretty readily tell that it doesn't look quite right. So the next thing you're going to do is, in this example, I actually changed the automatic mesh settings. So I sort of fiddled with them to make sure that they looked good. So in the next step, you can see what that looks like. And then I also wanted to go and add some local mesh refinement. So I know that those holes are where the part is going to experience the highest stresses. So that's where I want to make sure that it's really accurate. So I went, added some there, and then the next step is I added some local mesh refinement to the faces to make it work out a little bit better. In the next step, you can see how those compare now. Looking at the original mesh and this one, you can see that this is a lot better. It's much finer around the holes. And in other places, and it looks a lot better. And so now I'm pretty happy with this mesh, and I'm going to do the analysis. One thing that's important for meshing if you're doing advanced parts is something called mesh convergence. So as your mesh gets finer and finer, it stops changing. The results settle down. I didn't show that, but I did do that with this part, which is a good way of understanding that your results are actually correct. So now we've done this example, and we find that the stress, the maximum stress on this part is 115.8 megapascals. And I know that that's sort of above our threshold. It's above a factor of safety of 2, which is what we were looking for on this part. So let's see if we can take away some material and see if that makes it any better. So first thing to do is to do some cutouts on the arms. In the next slide, you can see that we do a cutout at the base. And then keeping the same settings, doing the analysis again. So in the next slide, we'll see the results. Here we are. So now we have a maximum stress at about 150 megapascals. And I know that that's a factor of safety of about 1.8. And the question is, so on the next slide, we can sort of discuss what these results mean. The question is, well, is a factor of safety of 1.8 acceptable? The first question is, can we trust them? And as I said, we can trust this example. We sort of use the highest stress that you could produce with your leg. In emergency braking that was tested. Doing mesh convergence makes us pretty trusting of the results. So now we ask, does it meet our criteria? Well, a factor of safety of 1.8 is acceptable in something like aircraft manufacture, but only because they spend a lot of money and a lot of time doing very good machining, and they source their metals very well, and they know that everything's perfect. It's very expensive to do that kind of things. And so we also are probably not happy with maybe the brake pedal being a factor of safety of 1.8. That's a really important part for your safety of the car, safety of yourself. So maybe we want a bit higher factor of safety on that. How will this work in real life? We suspect that it won't fail when you step on it, but again, we want to be really sure. This is a very important part. So we're actually going to probably go back and this now it's, do we need to make design changes? Well, certainly our final example or our final iteration isn't good enough. We're not comfortable with that. But you need to use your sort of engineering intuition and engineering understanding to decide where to go next. Should you maybe make those cutouts smaller? Can you fiddle with some pieces to make it better and make yourself happier with the results? And then test it again, test it again, test it again, and you find out, really try and optimize and get to the part that you're looking at.
Great.